Good morning. Welcome to NextRev's weekly Power Hour series. My name is Alberto Masaroto, and I will be your presenter for today. This week's Power Hour is going to cover tips and tricks on Creo Simulate. This is only a part one, as we discovered that there were quite a number of valuable tips that we'd like to go over. So we will conduct the second part of this Power Hour next Friday. These are going to be recorded, and eventually they will be uploaded to YouTube. So if you do have any questions about something that we showed here, or if there's a colleague of yours that would like to see this, please reach out to our sales team, and they will provide you with the proper link. These are only visible to our customers, so they will not be visible to the YouTube masses. A little bit about our agenda. So we'll talk about who NextRev is, as well as the Power Hours, both those coming up and the ones in the past, and followed by our instructor-led courses. At which point we'll dive into Creo Simulate, some of the tips that we're going to have, and maybe why you would use Creo Simulate, at which point we'll go into the demonstration. I will give a recap toward the end and give time for a little Q&A session. If a question does pop into your mind while we are doing the demonstration, please feel free and type it into the questions dialog box, and I will answer those toward the end of the presentation. If you are having any issues with audio or video, please also type that in there, and I will make sure that I address that should that become a problem. A little bit about NextRev. We have been working with PTC since 2001. In fact, we are the sole provider of PTC training on the entire West Coast. This means not only do we do the training for our own customers, but we also do the training for PTC customers. We have 6 mechanical engineers on staff, as well as electrical engineers, that are working with both Creo Parametric, Creo Elements Direct, as well as the entire Windchill line of products. We have well over 1,000 customers, and we do pride ourselves on the local support that we're able to provide. So the Power Hours that we have had in the past are all on our YouTube channel. And again, this YouTube channel is private. So if you want access to this, please contact your sales representative. If you do not know who your sales representative is, please email sales@nextrev.com, and it will be channeled to the proper person. The Power Hours can be found at nextrev.com/training/power-hours, and you'll see the Power Hours that are coming up. These Power Hours are customer-driven, so if you have any questions on types of Power Hours that you'd like to see, please reach out to us, as we always enjoy getting some additional feedback on what people find interesting. The courses that we offer can be found at nextrev.com/training. Please note that although we have a number of courses listed on our website as well as through the PTC website, this does not mean that those are the only courses we have to offer. We do train in the entire gamut of PTC software. In fact, we are a 100% PTC certified training partner. We are also one of the only partners in the United States that trains in Creo Elements Direct, formerly Co-Create. We would gladly do a training on site for any number of people that you would like to send to our facility, but we can also have these training engagements at your facility if that is more cost-effective and decreases the amount of time that your engineers are not working. We can also have customized courses. For example, if you have a number of people interested in the introduction to Creo Parametric, but your company also uses advanced assembly, surfacing, as well as PDM Link, or maybe the new PDME, right there we're talking about almost 3 weeks worth of training. Okay, it's very costly to have an engineer not working for 3 weeks. Thusly, we can provide a custom training class suited to the tools that your company uses, and take that nearly 3 weeks worth of training and knock it down to about a week and a half. Please reach out to us if this is something that sounds beneficial, and we'll gladly work with you on taking care of that request. So a little bit about Creo Simulate. Creo Simulate is going to allow us to work with the products that we're designing and leverage the digital tools that we have so that we do not need to print out prototypes, have prototypes manufactured. It will dramatically save time on waiting for these products to either be 3D printed or manufactured. But most importantly, it is a huge cost to have multiple prototypes manufactured. Simulate will digitally simulate all of these stresses that you apply to that part, and therefore, although it may not eliminate the need for a prototype, it will dramatically reduce it. The problems I hear oftentimes with structural simulation is that structural simulation tools typically require someone whose job it is to conduct FEA analysis, and that is it. Creo Simulate is not quite that way. Also, the issue of having a CAD tool that is going to create your model and passing it on to an FEA solver do create a disconnect. The problem that occurs when you have to edit the original CAD model and it has to be completely recreated in the FEA tool. And typically FEA tools do not want to deal with rounds and chamfers and complex geometry. Therefore, we have to tone down or dummy down the model. On top of that, since if an engineer who is not used to an FEA tool has completed an analysis, the question of competence comes into play. Was it meshed well enough? Did it actually converge? Is the resulting stress, are the resulting stresses accurate? Creo is not going to give you these concerns. The reason being, since Creo Simulate is integrated into Creo Parametric, the ability to go from one part to Creo Parametric, to Creo Simulate, is instant. There's no such thing as exporting and re-importing, and also making changes to that model in Creo Parametric will automatically reflect those changes in Creo Simulate. You just have to rerun the analysis. Because it is walking you through the entire setup process, you have the ability to rely on the results. This is going to mean that we have significantly fewer prototypes, which reduces time and reduces cost. Creo Simulate does not require someone to only have an FEA background. This is designed specifically for any engineer to run and use. On top of Creo Simulate, there's also a thermal analysis tool as well as advanced Simulate, which will allow us to do vibrations and a number of additional options, which we will cover a little bit today. Okay, on to the demonstration. Let me make sure that there are no problems with audio or video. It looks like a little bit issue of audio here. Let me see if I can make this a little bit better. I hope this sounds okay here. Definitely crank up the audio or the speakers on your computer. Maybe that'll help a little bit. I do apologize if the audio may be a little bit quiet. Okay, let's dive into the demonstration. So we have a few things that we're going to cover today. We're going to talk about meshing, simplified reps, fasteners, welds, and sensitivity studies. So let's get started here. Now, for those of you who are not used to the Creo interface, I do want to take just a moment and take a look at what we have here. So the Creo interface is the new ribbon-based Microsoft interface that maybe you've seen using the Microsoft line of products from 2007 to present. This interface very nicely groups all related tools together. The beauty is now anything model related is under the model tab. You go to the Analysis tab, everything analysis related is there and is visible. No longer do we have all of these menus and submenus and flyout menus. No, everything is right there and available to you. Now the thing is, if you are new to Creo Parametric, maybe it's a little bit difficult for you to actually find the tools that you're looking for in here, but that's not a problem. In the top right, we have a magnifying glass. This is called the command search. The command search will allow us to very rapidly find anything that we are looking for. Let me give you an example. Let's say we're looking for a family table. Just by typing in the first portion of family, if I hover over family table, we'll notice that under model, the model tab, which is in the top left, the model intent group, you will find family tables. Okay, so what I want to focus on here, since we're working with Creo Simulate, is where the heck Creo Simulate went. We hover over this, you'll find it under Applications, and there is Creo Simulate. Now, before we even get started, I want to focus on simplified representation. Oftentimes, people feel that simplified representations are used for assemblies, and that is probably one of the most predominant uses of a simplified representation. The question is, can the simplified representation be used elsewhere? So what we're going to look at now is taking a rather complex part, in this case here an injection molded piece of plastic, and trying to trim the fat. Okay, so let's just investigate this a little bit up here. We can see that we have quite a few rounds. I mean, they're kind of everywhere here. As we further investigate, there's all these little ribs that hang off the bottom. A lot more rounds in here. These two towers in the front. Again, we're looking at rounds everywhere. So what we should do is try and trim off the rounds where we don't need them. So if our structural analysis is focusing on the front part of this chassis, maybe looking at stresses localized in this area, why do we need rounds back here? What we're going to do is create a simplified representation by picking a round, right-clicking on it, and setting the representation to exclude. Okay, this is going to kick that round out of there. You have to give it a second, and you may discover that you will run into an issue with a failure if there is a round that maybe another round is referencing. So just make sure that you basically create a simplified representation from the bottom of the model tree up. That's probably the easiest way to do that. So what I'm going to do now is I've already taken the liberty of doing a simplified representation. I've created one called Simple Chassis. I'm just going to double click on that. I will notice that many of the rounds are going to go away. Let's give it a second to generate. Okay. And we can see there that we have a lot more of a rigid surface here. Okay. This means when we mesh the model, it will mesh much quicker since it doesn't have to focus on a tremendous amount of rounds. On top of that, due to the curvature of some of these rounds, you may get geometry that you are not able to even mesh. So trimming down the model features that we don't need is going to make the model run the simulation quicker and even allow a complex model to be meshed that maybe wasn't meshable before. So I'm going to focus on a different model here. So I've created a couple of representations of this particular model. This one here is just kind of a platform. And I'm going to go to Applications and click on Simulate. So give it a second. And you can see I have taken the liberty of applying a number of parameters and loads and constraints and material properties here. So just note that the first thing that you have to do to even run an analysis is to make sure that everything has a material property. Now, if you go under Model Setup, we'll just take a look at this real quick. We can have a default bonded type of interface, free interface, or contact interface. A bonded interface, let's talk about this here. So this front feature here, and this, what is this real fast here? This is nothing more than an L bracket bolted to another L bracket. Once we bolt this bracket to this bracket, just imagine that the two faces are touching. By default, Creo will assume that those two faces are bonded. We can find that under Refine Model and Review Geometry could apply. So the way that I currently have Creo Simulate set up this model here is these interfaces are bonded. Think of it like super glue. They are super glued together, but the glue is effectively infinitely strong, so there's no such thing as movement. Technically, Creo calls it infinite friction. So these two faces are effectively a single face. Now, that's not necessarily how it works in real life. We can set a free interface where there is no interface between the two. We can set that under the interface icon right here. We can specify interface, free, bonded, or contact. We'll talk about contact in a minute. We can set free, pick this face, and this back face, hit OK, and now they are free. Let's take a look what that actually means. We'll go to Review Geometry once again, apply. Okay. Now notice that there is no interface. This is accurate. If there is no bolt here, which we don't see a bolt, if there is no bolt and there is no interface, this panel should fall off. Okay, that is accurate. Now, we do want to put a bolt in, and we'll get to that shortly, but there is one additional interface called a contact interface. Contact simply means, okay, it may be a little bit difficult to see, but we have this plate, this top plate right here. Contact means if you put a contact interface between the bottom side of this plate and the top side of this piece of angle iron right here, they are not currently touching, but under a load, it is possible that contact could occur. So when contact occurs, by default, with a free interface, this plate will pass through this angle iron. That's not how it actually exists in real life. So we will basically put a contact interface so that when this top face and this bottom face intersect, there is a contact, and you will see deformation on this L bracket, or angle iron, excuse me. Lastly, what we want to talk about are bolts. Now, I've actually gone through the trouble to add my connections over here. I have a number of interfaces that I have applied. We can expand fasteners as well, and I have a number of fasteners that are suppressed right now. Now, there's a reason for this. I have conducted two analyses on this assembly, one with fasteners and one with a bonded interface to see what the difference is. Okay, what we're going to do is let's put a fastener in. Okay, so we're actually going to find that under interface, and we're going to actually put a fastener, which is right there. Okay, we see that. Now there are two kinds of fasteners. There's a bolt and a screw. A bolt, think of it as a bolt with a nut on the other side. Therefore, you actually have to specify the front edge and the back edge. Let's see what that actually means. Okay. This is the front angle iron, and this is the horizontal one. This back face here is the vertical angle iron. It might be easier to turn your view to shaded with edges so you can see those defined edges. I'm going to pick the first edge. Think of where the shoulder of the bolt goes, and then the interface of the nut on the other side there. Okay. Now we can have a frictionless interface, or we can, with this not checked, it has infinite friction. Basically what that means is the front plate and the back plate will not slide. By default, we do not have preload. This means when you thread the bolt in, think of it threading it in by hand. That's about as tight as you're going to get. There is no preload. So technically speaking, you would be shear. Not checking frictionless interface would have shear. They just don't call it that, unfortunately. If you do want preload, we can check that box. Please note, preload is not in the base package. So if you do not have advanced simulate, you will not have preload. Okay, so that's all I'm going to do. Hit OK. And in this case here, I did apply that bonded interface. So all it's saying here is it's going to undo the bonded interface because you can have a bonded interface and a fastener interface colluding together. Okay, so there's my fastener. Now I have gone ahead and added all of these fasteners already, so I didn't want to waste your time adding 25 different fasteners here. Let me go ahead and delete this. Okay. Now, I need to mesh this. Technically, I really don't have to mesh it, but if I don't mesh this geometry, it's going to take, the mesh could fail when I'm in the middle of creating, a analysis. Okay, so if I've gone ahead and run the AutoGen here to actually create the mesh, this is going to take a minute. So while this is sitting here creating the mesh, let me go ahead and go back to my presentation because I did take a picture of it already, so that might save some time. Okay. So when meshing, this is what you're going to get. Creo does a fantastic job of auto meshing. The way it auto meshes is certain areas that have more features, maybe more rounds, chamfers, bolt faces, sharp edges, will mesh to a greater resolution. This is adjustable. Okay, you have a minimum edge and a face minimum. The edge, by the way, is nothing more than a length value. So 5 in this model happens to mean 5 millimeters. Those are my units. Face min works the exact same way. So if you feel that you want to have a tighter mesh, or if you want to run the analysis very, very quickly, just to get an idea of how it looks, you can increase this. And the aspect ratio simply means that it's a ratio of the little it's a little bit maybe hard to see here. Each triangle has a max aspect ratio. This is why you have the ability to adjust this so that the triangles can be larger or smaller, depending all on the results that you want to get. If you want to just throw some quick results together to see if your assembly is on the right track, then I would decrease the resolution, quote unquote. If you've done a number of tests and the analysis is going in the correct direction, increase the resolution if you'd like, and you'll get a more refined model. Let's see if Creo is done meshing. So we can see, let's kind of zoom in just a bit here, and we see that the mesh has done its best to focus on these bolt holes. Okay, and this is going to be necessary when we actually run the analysis because we are running 2 analyses, one with bolts, one without bolts. Let me close this, and I did not show you how to actually go to the AutoGen results. We expand that, I'm sorry, settings. We expand AutoGen, we can go to settings. And this is where you'll find everything here, and there are your limits. Now, this particular model is a simplified representation of the top level. I got rid of the garbage that was up top. I got rid of some other features I didn't need. In fact, you can see that this little region, which is a surface region that I drew, is where the assembly is fitting. That's why we have the force specifically on those faces. In fact, the force is at an angle. This will reflect how the loads are applied to these bases as soon as we run the analysis. Also, I do have gravity turned off, so this is going to also affect how the analysis is run. Now, I'm going to go ahead and take a look at some of my analyses. And the first one, now there are several in here. We'll talk about modal analyses and maybe shock in the next week's presentation. Right now, I want to take a look at this static load one. Actually, we'll go with bonded first. I think we're both. Let's go with bonded first. And this, in the interest of time, I have run the analysis. Let's take a look at it. Let's go to stress, KSI, and turn on our tones here. Okay. So I want to focus on a few things here. I want to focus on the displacements. And remember, this is exaggerated here, okay? I did exaggerate this to 10 times. But I want to look at the bolt holes. Let's rotate this bad boy up here. The load obviously is being forced in the Z direction. So basically, there is a shear load on here. So let's kind of zoom in to an area where we are going to see a bolt. All right. That's pretty good there. I'm going to stop this roughly like so. Okay. Now I'm going to go back and open up another analysis. This time we'll grab the bolted analysis. Make sure everything's set the same way. To make sure your working directory is set to the location where the analyses live, they will automatically show up. All right, so it's in here. Let's focus on this little guy. And just get to the right spot here, and there you have it. Now, I'll try and orient these as best I possibly can so you can see both of them here. Okay, 1 and 2. Now, same corner, same loads. On the left, we have a bolted on the left we have a bonded connection. On the right, we have a bolted connection. Notice the increase in stresses around the bolted connection. Here they are very, very slight. This is here on the right more accurate, obviously, since in the real world, the bolt is what is going to force this plate to retain there. We're not going to have this fictitious bonded surface. And it's possible that you can use a bonding agent. I'm not saying that you cannot do this. Just know that in Creo Simulate, a bonded surface is infinitely strong. It's glue with infinite strength. Okay. I'm going to go ahead and close this. And one thing I want to focus on for a moment is something that we get a lot of calls on. Okay. Welds. Now, I get a lot of calls on both welds as well as creating welded interfaces in Creo Simulate. So the first thing I'm going to do is get rid of this the lid. And again, I've created a simplified representation already with no lid. And I've placed some welds in here. Let's actually investigate these welds. Okay. The weld looks like a surface, but again, this is not just a piece of geometry that I placed in here. If you look at the model tree, there is a weld there. What we will do is I'm going to go ahead and just hide one of these real quick here. So I'm going to roll this back up. There we go. Okay. Let me get rid of all those welds, just for the time being. I'm going to go to my Applications tab, and there is welding. The welding tool is very, very straightforward. So let's go ahead and this is add a fillet weld. Now there is a weld wizard, but in this case I think it's pretty simple to say, okay, well we know that we have to have a fillet weld in there. So I'll pick fillet weld. About the most complicated thing you're going to have to run into here is how to pick the surfaces. My recommendation is expand location, take surface 1. If you press Control and keep picking, you press Control while the first face is done and pick the second face, it will add it to side 1. So if you wanted to weld between the two sides, it's not going to work. So go ahead and clear. You have to pick it, pick side 2, and there's your weld. Or, then we'll clear everything. Pick 1, get rid of that, pick 1, right-click, side 2, and there is your weld. It is giving me a default of 6 units, and in the interest of time, I'll just say that's fantastic. Let that be there. Now I would place 3 additional ones, 1 at each corner. But I also want to go back to the fillet weld, and we have this option right here. Let's click on, actually before we do that, I'm going to pick this face and this face. Okay, it's giving me a fillet weld around the entire face. And that's nice and all. Let's see if we can actually edit that a little bit. Let me go back to that fillet weld, edit the definition, and click on this icon here. This icon will allow us to actually split the weld. So I can say that I want a total of 10. Each width is defined right here, 1 millimeter, probably a bit on the small side. Let's make it 5. Green check mark, and there we have it. So this will allow us to do these split welds. I tend to forget every now and then what the industry calls these types of welds. I haven't dealt with that very much, but this will allow us to very easily create these welds. Now, in Creo Simulate, it does treat these welds as a single weld. Let's reactivate these. Okay, and this is what we're looking at here. I'm going to go ahead and go back into my application, go to Creo Simulate, and I have taken the liberty to apply some loads on these surfaces, some constraints here on the bottom, and the welds have also been applied. So let's just expand connections, and we'll find all of our welds here. And for the time being, I'm going to simply suppress these welds here. So let's go ahead and you need to find the weld tool. It's not one that I use often, so we'll just use the command search. Hover over it, and there it is on the refined model, and I can activate it as well. Now, by default, Mechanica is going to assume you're going to define a weld in Mechanica or Creo Simulate. If I click on this specify weld feature, I can pick the weld feature. I did not define a material for this, so instead of getting out of the tool, I can simply say override weld feature settings. The thickness is 6 millimeters. That is the thickness that I applied in the weld feature, but I could also say, you know what, the person that designed the model and placed the weld made a mistake. This actually should be about 2 units thick, and that can be edited here. And then you can specify your material. The material choices are the same ones that you specified for your materials in Simulate, but you can also add some more. Okay, and there is my weld connection. Same thing over here with these 6. We'll come back over here, go to weld, pick one of the 6. Before we do that, we have to type the weld feature. Pick one of the, actually there's 10, I believe, not 6. Pick one of the 10. We'll again override it because we have no material properties. Hit OK. And let's take a look at our geometry. I'm going to go ahead and review geometry. And note here that it does see the interface between the weld and the feature as bonded, and that's accurate. Technically speaking, Mechanica, Creo Simulate is not going to show the weld snapping off. So that is an infinitely strong weld between those 2 edges. Okay, and just because it is showing those 2 edges does not mean it's not including the inside here. Creo Simulate was well aware of how a weld functions within the model. So hit OK. And I'm going to go get rid of these two and reactivate our previous bind. And again, I have gone through the liberty of creating a analysis already, so we'll go to our analysis tool. I may need to set my working directory, so just bear with me a moment. Like I said, it is important that you do set your working directory, otherwise it won't actually do this. So there's our working directory. We may have to reload this. Give me 1 sec while I do that. Actually, no, we'll just go ahead. We actually go ahead and just run this analysis here. Let's go ahead and load the analysis. Let's see it in there. Okay, we'll just go ahead and rerun the analysis. I made it pretty quick, so it should take no more than a minute to run the analysis. So this is analysis 1. We are going to just do a standard analysis. So I'll run that real fast. And all I did was just do an analysis where the base of the feature is simply locked, and there is a bearing type load around this feature here. So let that be for a moment. And ideally, I didn't change anything that is going to give us a failure. So anyway, we're going to run the analysis, and the reason why the analysis actually has to be run, fantastic. The reason why the analysis has to be run is that we want to do a sensitivity study. So without an analysis to point to, we actually can't have the sensitivity study. And let's take a look at what our results were. Okay. And let's make the animation get a bit slower here. Let's go back. It's going to be a bit difficult to see the gaps in here because the whole thing is blue. Anyway, we are seeing the stresses between this weld and this face, and how well it can be seen. But we do see the weld stresses right there, as well as the stresses on the face due to the weld kind of being pulled on it. I'm not too thrilled about how this ran. Actually looks a little bit better down here. I only did a single pass adaptive. In this case, you might want to increase that to multi-pass adaptive so that we can get some additional accurate loads. Right now, the meshing is very, very light around these areas here. But this is giving us enough foundation to actually create our next feature. Let's close this up. Okay, and the one I want to focus on is the global sensitivity study. So I'm going to right-click on this and go ahead and edit it. Actually, you know what? I'm going to do something a little better. Let's get rid of this entirely. Let's make a new one. Go to File, Sensitivity Design Study. Pick an analysis. We'll do this analysis one that we just did. That was a static analysis. And then I'm going to come over here and pick on a dimension. Okay. This is going to ask us to select a feature that we want to focus on. So in this case, I'm going to pick on this weld. We have a length, we have a quantity, and I'm going to pick this particular quantity of 10. The current value is 10, and I can say, you know what, I don't know if we want to have 8 of these or 50 of these. So I'm going to say, okay, I'm going to start at 5. And I want to go as high as 15, okay? So this simply means that I do not have to change the value to 5, run the analysis, change the value to 6, run the analysis. Creo will do that. It will say, okay, we'll start at 5 and work your way up to 15. And hit OK, hit the green arrow, and it will run the analysis. Unfortunately, we do not have enough time to run the analysis. But that's all you would have to do to create a sensitivity study. The big part of this is that you need to actually make sure that there's analysis to reference in order to conduct the study. Otherwise, they won't even let you do that. Okay. The first thing that we talked about was simplified representation. Although we can use a simplified representation in a assembly, and most people do, a simplified representation is going to allow a model to mesh significantly quicker, or even mesh if the top-level model doesn't mesh within Creo Simulate. Okay, focus on the areas that you're interested in. The features on areas that you're not interested in can be omitted because you're not going to play any significant role in your design. I did mention that I ran a single-pass adaptive mesh. Now, a single-pass adaptive mesh will automatically do a third polynomial equation, basically this one right here, the third equation. A multi-pass adaptive mesh will start with a single-level polynomial equation all the way up to a ninth level polynomial order equation. Just remember, the higher the order, the longer it will take to complete the operation. Under limits, you'll see convergence. The lower the convergence, the longer it will take. In fact, it may even have the ability to not converge. So I think a percent convergence of about 10 is pretty good. We talked about how to mesh. Meshing is always nice to do before you run the analysis because it will at least let you know if the model is able to have an analysis run on it. If it can't mesh, the analysis will fail. Bonded versus bolted is a big one here. By default, Creo is going to give you a bonded interface. You can specify a global setting to make it free, and that might be a little bit simpler to, instead of omit the bonded interfaces, just say start with a free interface, and now I'm going to add my bonded, my contact, or my bolted interfaces. And then note that on the left, we are seeing a lot more stresses on that bolted interface versus on the right where we have a bonded interface, and effectively are seeing no stresses. So with welding, we have to recall that we weld in the model, and then Mechanica, or Creo Simulate, is able to detect that is able to detect that weld in the model. Okay, it's a weld as a feature. You select the feature. This way you do not actually have to place the weld in the simulation, although you can. And then your sensitivity studies. In this case, I simply selected this weld, where each leg, I think I had a quantity of 10 legs, and I changed that quantity from 8 to 12 in this sensitivity design study that you're looking at here on the screen. This will allow me to run through a series of operations so I can see all the different stresses between 8 and 12 in this case. Well, thank you very much for watching the presentation here. I'll go ahead and open the floor up for some questions. I apologize, my question box is about 3 pixels tall. Let me scroll up over here. You said we had a video issue for a split second. I'm glad that stopped. Okay. I have a question on gravity. Do you have any tips or recommendation on applying gravity as you did in the paper model? That's a fantastic question. It depends really on what you're building. If you're building something that is very, very robust in general, and you're just looking for a certain kind of, it's a difficult question to answer because it all has to do with what you're trying to build. That table, for example, was very, very large. I think each beam was 3 meters, so it's a very husky piece of metal there. So naturally, gravity is going to play a role in how that plate on top fits on those other brackets. Now, if you're talking about a piece that's maybe 3 inches wide, gravity, sure, gravity always takes a role on whatever we build, well, unless we're working for NASA. Because it's gravity. But if it's something very, very tiny and there's not going to be much gravity in general, that's just a constraint that's going to take time. So let me show you where I actually applied that. In a sec here, I'm going to pull the model back up. Okay, let's go back to applications, simulate, and gravity. Okay, so gravity is right here under the loads group. Of course, the box up here right behind where I'm working here. Okay, here we go. So here's our gravity, and this is a pretty simple one to apply. It's really not looking for a place to put gravity. However, it does want to know what the direction of the gravity is. Remember, we're looking at this model. If I'm going to hit Control-D to get the default orientation, this model, I'm going to turn on my coordinate system as well. We see that the coordinate system Y is in the plus direction, X is to the right, Z is going down, and by default, gravity will follow that. So gravity Y will be against gravity, minus Y is the direction that gravity is going. So we can open this up over here. Obviously, millimeters per second squared. I always worked in meters per second squared. Right here, it's 32.2 or 9.81 feet per second squared. We could just type in the minus Y. 32. It is 32.2. Right? It's been a while. 32.2 in the minus Y direction. Now, this is the world coordinate system. I could also specify a, oh my God, you're right, 32.2 feet per second squared. All right, sorry, 9.81. Okay, I got that. No, that's wrong. 0.81. There we go. Thank you very much. All right, 9.81 meters per second squared in the minus Y. Y being, I don't know how well you can see that coordinate. Let me zoom in so it's a little bit more visible. There we have it. So now we would apply gravity in meters per second squared, and we will be good to go. So hit OK, and gravity is applied. And again, on this part here, this is a fairly small part. I think the overall length of this is no more than a foot. You know, it really depends on if you feel gravity is going to apply a significant role in your model. Even if you don't think it's going to apply a significant role, you just want to put gravity in because gravity, after all, is all around us. It is an additional constraint, and it will take a little bit more time to mesh. But, you know, that may not be a big deal. I hope I answered your question. Thank you for the clarification on the 32.2 feet per second, not meters per second. It's been a while since I've done that. Okay, looks like those are all the questions. It looks good. All right, well, I hope everyone enjoyed today's Power Hour. We will be doing a part 2 of this next week. I believe I'm also one doing the presentation then, so I hope you enjoyed it. Have a nice, this is Memorial Day weekend, right? Have a nice weekend, and everybody be safe. Thank you very much. See you next weekend.